About this as this angle change. The potential energy starts from the high point. Okay? So if this is theta, okay? And you are going to substitute this, okay? Then you are going to have a square of that. Okay? A square of that. Okay? Is it going to be greater or lesser? Depending on it's more than the angle itself. Okay? So this is a square. So you see, when angle change from high to low, the potential energy also change from high to low. From the angle change from 0 point to very low, this potential energy however change from 0 to a high, is it? Yeah. So this is only half of the cycle, but the potential energy already changed by one cycle. Okay? Why is that the case? You see here, angle is a sine function. Okay? However, the potential energy is mg h, and h was derived to be, supposedly h is L1 minus cosine theta. We derived it yesterday and find out this is mg half L theta squared. And this theta squared upon substitution is mg half L capital theta squared and sine squared omega n plus phase. Okay? So look at here. Why the period? Okay? This is not the square. I should do the correction. Okay? So this will appear something like a double sine. Double sine wave. Yeah, this is the square. Okay? Why is it double sine? Remember sine square. What is sine square? What is sine? Okay? If you recall, you can obtain sine square from where? Cosine theta, cosine 2 theta is what? Cosine 2 theta is cosine square minus sine square. And what is cosine 0? Cosine 0 is equal to 1 is equal to cosine square plus sine square. If you now want to find the sine square, what should you have? You should have the second equation subtracting the first equation. So your sine square is now equal to half 1 minus cosine 2 theta. Okay? Yeah. So that is the reason to tell you why angle is taking a period. Okay, during that period, your energy already changed twice. Okay, so this is sort of like the blue line is a sine wave, but this white line is 1 minus cosine 2 omega t. Okay? You can also see that the equilibrium point for the sine but this square will have the neutral point being non-zero. Okay? Yeah. So this is an additional term. So it's being elevated by half. OK， 好，我们刚刚讲完的是你的这个单摆的摆动从左到右。如果摆角 ，OK， 如果这图是一个大的 θ，OK， 然后它花的这个完成一个周期的时间是 t，OK， 所以它会从一个高值到零，再一个低值，然后再到零，然后最终到了高值的时候，才完成一个周期 ，OK。但是你如果用这个角度去算你的势能，红线对红线哦 ，OK。上面的红线是 sin omega t， 但下面这个红线是能量，它是 sin square omega t，OK。所以这个时候，这个 sin square omega t 呢 ，OK， 它的周期是多少？它的周期是这个原本角度周期的一半 ，OK， 也就是说，它在半个周期里面，它就完成了一次能量从高点到低点，再回到高点 ，OK。来，如果同学不懂，我再说，来，我们问一下。以单摆为例，为什么能量周期跟摆动周期，能量周期会比摆动周期短一半 ？Okay, why the period for energy is half the period of the angular swing? Okay, why the period of potential energy? 我们来问一下，来后面的同学，以单摆为例，是的，来后面，
应该是因为它会来回。
来，如果同学想象不到，我们用一个单摆，对，我们用。摆动这个势能高位，然后回到来这个是摆动的一个周期，在势能的这个周期是摆动周期的一半。Why the period of potential energy change is half the period of the swing? 说明白一点，就是你如果是太大声，你表达很大声 ，you sing from one branch, you can reach another branch on the opposite side at the same time. So this height of the branch is what is define the potential energy. It need not come back to the same point. If it doesn't actually only do a swing coming back, okay, you never go and chase any other prey. Okay, so you must swing to the opposite side. This opposite side only happen for a half period of the swing. You already reached the opposite height. Same height, but opposite. Okay, so that's explaining that. You see, the angle take a period t. Okay, but the height will come back to the same height, but opposite. Okay, in half period time. Okay, 所以这个同学要懂得看这个书公式不是随便念的，你的公式本身跟它的物理意义你要结合，你才能掌握。OK。 next, let's look at the velocity. Okay? If I now replot the angle, okay? This is my angle, which is the sine function. And what is the velocity? After you do the time differentiation, you have omega n t. What is your angular velocity? It's not having the same amplitude as the angle. But this is the new amplitude of the angular velocity. That is omega amplitude of displacement. So if this is a sine wave, my cosine should be something like, is it this? Okay. Then I come to the zero at this point, and come to the peak at this point, come to the zero at this point. So I redraw it. Okay. So velocity will have a phase difference, phase lag from the displacement by 90 degrees. Phase lift. Yeah, this is phase lift. So when you have a peak here, so the velocity already dipped by 90 degrees. So that's how you see the velocity is a constant function. And now if you're going to do the calculation of kinetic energy, you're going to square the angular velocity. Then you pre-multiply it by the mass and half it. Then you have the kinetic energy, then it's half mass angular frequency squared times the displacement amplitude, angular displacement amplitude times cosine theta. And what is cosine theta? If now you want to get cosine theta, what you should do? You have equation 1 minus equation 2, then you have a cosine 2 theta minus 1 equal to your 2 times cosine squared theta. So your cosine squared theta is then half cosine 2 theta minus 1. Okay? Again, angular frequency has a period of 2 pi over omega n. However, if you look at the blue line, the kinetic energy chain has also peaked half the period of the swing, or half the period of the swing frequency. Why is that the case? If you take the example of the pendulum, 好，我们就看这个单摆，你这一个周期摆回来，为什么你的这个动能，它在这个一个周期里面，它峰值出现过2次，来，以此类推。So let's ask a question about the the 你看，你说看，辐射动能在摆动的一个周期里面出现2次峰值。
那它经过最低点就会到动能的峰值。
OK， 一次是顺时针的最低点，一个是逆时针的最低点。OK， so that's the reason. Okay, based on this, okay, our previous case is when we do the sum of these two. Okay, now I'm going to write the equation to prove the point. Okay, I think we did that yesterday, but you may not. You did not do by yourself. So if I just copy down the equation, half mgl theta squared sine squared omega nt plus phi plus half m omega n theta squared cosine squared omega n theta squared. Okay? This sum, okay, you can do the factoring out. What we do is we do factoring out when we do the sum. Okay. Square is there. Okay. This is GL sine square omega n e plus base plus omega n square sine square omega n e plus base。OK， 你的势能跟动能的和，OK， 就是这个式子，它是 sin square 平方，它是 sin square 平方。OK， 它合起来是什么？它合起来可能是任意的。OK， 它如果说势能的高度跟动能高度不一样 ，OK， 它合起来就是两个波，这样 ，OK， 但是有一个情况 ，OK， 比较特别，这情况是什么？这情况是你的 omega n 等于 GL， 我就有公式了。If you in the special case, when this is common factor, GL is a common factor, then you have this sine square plus cosine square, and of course this term is equal to 1. Okay? So this is valid in the case of free vibration. It's not valid during the forced vibration. What means free and forced vibration? So this equation is valid during this free vibration. So it's valid during free vibration. Okay? But if you are being pushed, okay? By force, okay. But they are swinging them at the right frequency, that's natural frequency. Okay? However, if you are forcing it at the frequency not at the natural frequency, then this is not valid. Okay? What is free? You got to be clear. Okay? So on that condition, so we realize one important thing. Okay? You are talking about the amplitude change. Okay? How do you get this omega n equal to GL? I can get this as the amplitude change. Why I say this amplitude change? This is because sine square, okay, will change between, this is what? Between what? Between, what can this be? Half minus cosine theta half. What's the change between this? Okay? This theta can change between positive 1 and negative 1. Okay? So the change of this will then between 0 and 1. Is it right? The change between 0 and 1. Okay? So I can say this change is 1. Okay? The change. Okay? So as a result, you can now see this is the change of my potential energy. How about cosine square? Yeah, it's about the same. Cosine square will also change between 0 and 1. Okay? And this is now my chain of kinetic energy. going to apply a Rayleigh method. Rayleigh method tell you, okay, you can determine the resonant or natural frequency by setting the chain of the potential energy to be equal chain of the kinetic energy. Okay, so that is the potential energy chain in red line, and that is the kinetic energy chain. Okay, red line. Okay, so the energy of the chain are equal. Okay， 哎，同学，请问这个 delta 是不是多余的？我可以拿这个 delta 吗？看，我们问一下这位同学。对，你看的这张图，一个是势能变化，一个是动能变化。OK， 我这个 delta 你看看。好，我们再问一下另外一个同学。都，哎，这个 delta 可以拿掉。Can we remove the delta? If we remove the delta, is this remain identity? 可以拿掉 delta 吗？这等式还成立吗？确定 ？OK。来，我们刚刚昨天这个帮忙做实验的同学，对，
这边应该可以吧？
可以 ，OK。So if you say it's okay, okay, then this is on the condition this is max, okay. When you say max, yes, you can. But can I further reduce? Say this is the same? Cannot. Okay? Okay, you cannot because of the timing. Okay? The timing is this is not equal. Okay? We're talking about max, yes. But max is still not quite right. Okay? Why am I saying max is not? This max is not quite right. In what situation this is not true? 来，同学看看，在什么情况底下，第二个式子是错的？
不是 free vibration，not free vibration，
没有，我们是跟他单板的例子。
是 free vibration。
在什么情况底下
data 不在最底边。
好诶，
data 那个你的 data 不是设在那个
最低点，答对。
蛋白摆下去的最底边。
OK， 看到没有 ？What defines the potential energy depend on the datum. The lowest point you set the datum to be 0, I think that's fine. But if you say, oh, this pendulum is at the height, which is non-zero, and then you define that potential energy, then you're not going to have kinetic energy equal your potential energy at the peak. So the more precise way of saying this is right, okay, is you are talking about the change. So the change, of course, is with reference to the lowest point. You see, zero potential energy to unit potential energy. Okay, so this is what you set. Okay, so I'm going to again. Let's take this one. This. 上课的 疑问可以拿来做考一样。Okay, so now you can know the difference. Okay. So next, based on this, okay, we now sure that what Randy say is right and generic. Okay. 这个雷利的这个公式，它是用能量的动能守恒，动能跟那个势能守恒的关系来找自然频率。So we are going to apply Rayleigh method to find this natural frequency. So what is that chain of potential energy? This is your half mgl capital theta times 1 minus 0 is now equal to half m omega n theta squared. So this is going to be half m omega n squared theta squared. Okay? So if you now cancel out a common term, then you find that sorry, this is not the omega to be cancel out. Yeah, the one cancel out is the amplitude. So after simplification, you have the GL. Does that mean something? Yep. What do I mean? Okay. So there was something missing. Okay. 那我们看一下，我们这个公式少了什么？Yeah, you have the L square. L square, is it? And then on the right hand side, I got the NG. No, this is right. Okay, and this I got the L square here. So you have GL L square omega n square. So this now omega n is equal to 12 of G over L. Okay, so this one I got to do the bracket. I got the angular frequency. This one must have L square. After you have that, then you have the common term. Okay. That is the square root. Yeah, correct. This is right. 好，同学看到没有？我们是通过这个式子，就得到雷利的方程。OK， 那它的 idea 比较简单。So how Rayleigh derive this? He didn't go through the example using pendulum. He didn't go to the detail. But what he's arguing is at the maximum potential energy. Okay? So it's equal to other energy state. Okay? So at the maximum displacement, so you only have potential energy. And then at the lowest point, you have the maximum kinetic energy. Okay? So here, lowest point, we will set a non-zero potential energy. Okay? So now, by applying energy conservation, you see that that chain of kinetic energy is equal to chain of potential energy. And that will be the chain of the kinetic energy equal to the chain of the potential energy. Okay, this chain being maximum, we're referring to the chain from lowest point to the highest point. Okay, it doesn't mean that, yeah, it is a chain halfway. Okay, there was a maximum chain. is the maximum change, not the maximum kinetic energy and not the maximum potential energy. Okay? Now you come back to our example. The potential energy is equal to the kinetic energy change. Equate the change, huh? Again, I have to remind you, it's the maximum change, not the maximum kinetic energy, not the maximum potential energy. Okay, so then you have this natural frequency determined. So would the theory apply to the other example? Yes, it can. Let's derive that. Okay. In this example, you have the spring, you have the mass, okay? Taking these as a position, and over the time, you have the translations, yeah. So because of the stretching, the potential energy is half kx squared, okay? And because of the mass storage, then you have half mx dot squared. And lag, the x is equal to the amplitude x sine omega t plus omega n. So this is the base, then define the starting point. So you then have the speed being omega x cosine omega n t as a phase. Upon substitution, then you have this half k amplitude square and sine square omega n t plus the phase. Okay? Upon substitution of the velocity, you have the half n omega n square and then square cosine omega n t square. Sine square, you remember, the chain is between 0 and 1. Cosine square is chain between 0 and 1. So based on this, now you can apply your Rayleigh method. Okay? The Rayleigh method telling you that chain of potential energy is this value. Okay, capital X squared. And what about the chain of the kinetic energy? That's the chain. Okay? Filtering out the common term, and now you can find what is your natural frequency. That's basically the ratio of the stiffness to the mass. So, okay. And also, please be reminded they got also some relationship you have to start getting familiar with. Okay? Stiffness. What's the unit of stiffness? Newton over meter. What's the unit of the mass? Is kg. What's the unit of the natural frequency? This angular natural frequency. It is what you call radian per second. Okay? Okay? And you square it. Okay? In that way, can you find that? K is the signal, can now be determined from the frequency. Okay? 是告诉你什么？你原本如果是一个弹簧，根据昨天的5个定律，我要调动量长度 ，OK， 那我才知道它的这个弹性系数。但是我现在不调重 ，OK， 不量长度，我就只是看它的画。如果我知道它的重量，我就知道它的频率。反过来，我就可以找到它的弹性系数。So this is how you can see things remotely. OK？ 为什么要找这样奇奇怪怪的东西呢 ？OK？ 为什么要用频率来鉴定它的弹性系数 ？OK？So why is it important? How to do the measurement of the stiffness directly? Why you have to use the frequency to determine the natural frequency and stiffness? In what situation you need to use the frequency to determine the stiffness, but not by using Hooke's law, by not applying law. 那我们来问一下后面的同学，来，这个公式很特别哦。来，你念一次，这个公式什么？好 ，A 等于这是在讲什么？来，同学帮忙。看有个同学有援助。这公司在讲，看前面。So what this formula is about? So what is about? K is equal to n omega n squared. 我们问一下后一，没有人，你前面，对，再进。这公式告诉你什么？
技术的质量是
对，角跟那个地方，自由振动。OK， 我弹性系数，我们做实验用5个定律啊，用调重啊。我为什么现在要用频率来找？在这样的情况底下，所以 what situation then you need to find the distance from the free vibration natural frequency? 来，后面下一个。
这样弹性，这样很难变形的那种。
OK， 那给的提示哦，这很难变形。
弹性系数非常大的，你要挂着重你才能让它变形。
是吗？是弹性系数非常大吗？来，是弹性系数非常大吗？还是哪一个极限情况？也不能来。弹性系数非常大的情况，自然频率是0，因为它是钢体，所以你也测不到。OK， 所以就是
在震动。
So in the case of very stiff material, almost rigid, okay, you still have to use Hooke's law, but apply more force. So this happens to the case where the material is so soft or so small that you cannot apply force accurately. Then you start monitoring using frequency. 举个简单的例子，你们有用微波炉吗？好，微波炉在搞什么？So did you use microwave? What's microwave for?
by vibration.
So what you have is, do you remember how it is hitting what? Microwave is used to hit what? It's used to hit H2O. How do you write this H2O? O molecule and the H molecule. Okay? Where do we have the mass? And where do we have the spring? Your mass is coming from this atom, and then the spring is coming from the bonds. Okay? So you are sending the microwave to excite this. Okay? As it excites, as it resonates, then you gain energy, then you get heated up. Okay? So this is also the way chemists are using the Fourier transform infrared to monitor what molecule you have. Okay? So they are inspecting the spectrum. Okay? The signal intensity versus the frequency. Okay? So that using frequency, if you now know my molecular mass, okay, then I can now go and predict how strong the bond. Okay? So this is how chemists are using your traditional vibration to sense what you cannot measure by force. Okay, you can't apply that force, but you can excite them to resonance. Okay, then you figure out the frequency, and you know the molecular weight. If you know the molecular weight, then you go to find how strong the bond. Of course, microwave is doing the reverse. Okay, I'm not caring about what's the strength of the bond. Okay, I only care about can I excite them into resonance. Then I'll send a signal, excite them into resonance, then you gain in the heat. Okay, think of one. So with this, now okay, we have the idea about the natural frequency determination using the energy method. Okay? So that is simply angular natural frequency squared is equal to the ratio of the stiffness to the mass. Okay? So is it just limited to that two simple examples? No. It applies to many examples, but on the condition that it's 1 degree of freedom. Okay? If you have multiple degree of freedom, then it's not that easy. You can use Rayleigh method. You have to use other method called Lagrange method. Okay? Yeah, Rayleigh is English, and then Lagrange is French. Okay. And yeah. Okay. Now that's why what do you define degree of freedom? If there is a mass in the spring moving in one direction, then you call it 1 degree of freedom system. But you also know that for a mass spring system, it can move more than 1 degree of freedom. Okay. So what you see here, 1 degree of freedom is because of my excitation. But I can also move it in a conical way. So if I move it in a conical way, so there is an oscillation, so you define it by angle, and there is a distance away of the spring, then you define by the length, okay? Then you have multiple degree of freedom, okay? And also, it is also possible that I can have this spring pendulum, okay? So in this case, the arm length of the pendulum is not constant, okay? While I'm defining the swing angle, I also need to define the length of this spring pendulum. Okay? So that would be more than 1 degree of freedom. So this is a simple pendulum. Okay, now next we come to one example. How can you determine a roller on the spring? Okay, and find out the natural frequency. What makes a roller? A roller, just like a wheel, it will turn. Okay, and you also know the moment of inertia. Okay, a rolling motion is best determined using the angle. Okay, so let's go derive that. Okay, and then now if it hits on to the spring, okay, how are you going to solve for the natural frequency? Okay, so you now have a roller or wheel. The center of gravity happens to be axis of rotation. Okay, and if you start turning by angle theta, then this will move by theta. So then x will happen to be radius theta. Okay. So let's play this as a video. Show that. So there's a recap of your diagram. Let's see here. When you learn this rolling motion, okay, let's spend some time on that first. What makes a rolling motion? Yep. Yeah, this is a rolling motion. If there is a wheel, yep, you can see the turning. Okay. Okay. So now let's come back. How do you model this thing? Okay. With this, we are talking about the kinetic energy as its role. Okay. So you have the self-rotation. Okay, theta dot. Then you can write the kinetic energy is half the mass and the outer radius square, angular frequency square. But at the same time, if you now look at it as a point mass at the center, this is moving horizontally. Okay? Then there must have a kinetic energy half m x dot square. Okay? And what is the x dot? X dot is x equal to r theta dot. So together, then you have half m r square theta dot square. So you now add them together, then you have mr squared plus half mr squared for your this total kinetic energy. Okay? So in that way, so now what is your equivalent mass? Your equivalent mass of a wheel is the mass of the wheel itself plus moment inertia divided by the radius. 所以你如果被一粒轮胎静止的轮胎撞了，你可能没事；或你如果是被一个高速旋转的轮胎撞了，为什么有事？ So why when you are colliding with a static wheel, you suffer no damage. But if you are colliding with a high-speed rotating wheel, even the wheel is made of rubber. It has no sharp edge cutting you. Okay? If you hit by such a high-speed rotating wheel, okay, you got the wound. Okay, 你被这样的轮胎撞到，你会有内伤。Okay, it's because of the kinetic energy. It stores more now want to analyzing, okay, what is the kinetic, what is the natural frequency of such a wave? What you can do is analyzing, okay, how much the kinetic energy change we already figured out, but now it hits on to a spring, okay? If you hit on to the spring, okay, that potential energy is half kx squared. Equal to half k radius squared theta squared. And now by equating this kinetic energy, okay, by equating half this, okay, then you're going to find out your natural frequency. According to Rayleigh method, okay, in the case of rolling wheel with no spring, in the case of rolling wave with no spring, the natural frequency is 0。所以你轮胎一直在滚，没有弹簧的话，自然频率是零。Okay? But if you now hitch onto the spring, okay, because of this extra elastic potential energy, you equate the chain of the kinetic energy chain to the potential energy chain. Okay? Then you can find out, my natural frequency is 2/3 times k over n. Okay? So this means a rolling wheel will carry more energy than a sliding wheel. Okay? And yeah, so in that way, we use the Rayleigh method to find out these free vibrations. Okay? And yeah, that's it for today. And also, for the homework, it is due on